Hi, in this video of import, we'll study results on dimension of subspaces. The first result relates the dimension of a subspace to the dimension of the vector space which contains it, and then we shall see a corollary about the extension of a basis of a subspace to the basis of the vector space. So the theorem says that the dimension of the subspace of a finite dimensional vector space is always less than or equal to the dimension of the vector space. So let W be a subspace of a finite dimensional vector space V, then W is finite dimensional and dimension of W is less than or equal to dimension of V. Moreover, the theorem says that if dimension of W and V are equal, then V is equal to W. So let's prove this theorem. So we let dimension of V to be equal to n. Now if W is the singleton set 0, then W is finite dimension, then W is finite dimensional, and dimension of W is nothing but 0, which is less than or equal to n, so the result holds. Otherwise, we have a non-zero vector in W. So otherwise there exists a non-zero vector. We call it x1 in W. So because x1 is a non-zero vector, so the singleton set, then this singleton set x1, this is linearly independent. Okay, now we've got this linearly independent set. Now we can add more vectors from W to this set such that the resulting set is linearly independent. ठीक है, तो हम क्या कर रहे हैं, इस set x1 को हम बड़ा कर रहे हैं, तो हम इसमें और वेक्टर्स ऐसे ऐड कर रहे हैं कि तब तक ऐड करेंगे जब तक सेट लीनियरली इंडिपेंडेंट रहता है. सो वी चूज वेक्टर्स x2, x3 and so on till xk in W such that the set x1, x2, xk, this is linearly independent. Now this set x1, x2, xk, this is contained in W and W is a subspace of V. So this is a linearly independent set in V as well. Okay. So this set x1, x2, xk is linearly independent set in V and V का dimension क्या है? V का dimension हमने n assume किया था, तो V में कोई भी लीनियरली इंडिपेंडेंट सेट में n से ज़्यादा वेक्टर्स तो हो ही नहीं सकते, ये हमने थ्योरम में प्रूव करा हुआ है. सो एज डिमेंशन ऑफ V is n, no linearly independent subset of V contains more than n vectors. So that means k should be less than or equal to n, right? And this implies the set x1, x2, xk, this is linearly independent. But if I consider the set x1, x2, xk union a singleton set V, where V is not equal to xi for all I, less than equal to k and greater than equal to 1, and v belongs to w, then this set is लीनियरली डिपेंडेंट. ठीक है, हमने ऐसा k चूज करा है कि ये सारे वेक्टर, ये सेट जो है x1 x2 xk, ये सारे वेक्टर्स तो लीनियरली इंडिपेंडेंट हैं, लेकिन अगर हम कोई और वेक्टर चूज करें तो ये जो नया सेट बनेगा वो लीनियरली डिपेंडेंट हो. सो बिकॉज x1 x2 xk union singleton v is linearly dependent for any v in w, so this implies that this v belongs to span of x1 x2 xk. This theorem we have already done, that beta union singleton v is linearly dependent if and only if v belongs to span of beta. So this implies v belongs to span of x1 x2 xk. And v was what? V was any element of beta w minus x1 x2 xk, right? So this implies w is contained in span of x1 x2 xk. और क्योंकि x1 x2 xk ये जो थे ये w के ही एलिमेंट्स तो थे, तो इनका स्पैन जो होगा वो भी अल्टीमेटली w में ही होगा. तो w क्या हो गया? स्पैन ऑफ x1 x2 xk. So this set is a spanning set of w, and it is linearly independent by our choice, and so this is a basis for w. So this implies the set x1 x2 xk is a basis for w. Now so the dimension of w would be k, so this implies dimension of w is equal to k, and k was less than equal to n. So we are done with the first part. Now we have to see that if dimension of w is equal to dimension of v, then v should be equal to w. So now we consider that dimension of w is equal to dimension of v, which is equal to n, and let beta be a basis for w. So beta will have n elements, right? So beta contains n elements, and beta is linearly independent in w and hence in v. ठीक है, क्योंकि बीटा लीनियरली इंडिपेंडेंट w में, तो बीटा लीनियरली इंडिपेंडेंट होगा v में. अब हमें v का एक ऐसा सबसेट मिल गया विच कंटेन्स n वेक्टर्स एंड इट इज लीनियरली इंडिपेंडेंट. सो बाय corollary of replacement theorem, the second corollary of replacement theorem, we have beta is a basis of v. So w, which is equal to span of beta, it should be equal to v, and hence we are done. So we have a corollary to the previous theorem. It says that if w is a subspace of a finite dimensional vector space v, then any basis for w can be extended to a basis of v. So we can extend any basis of a subspace of a finite dimensional space to the basis of the vector space itself. So the proof is very simple. So we let S be a basis for w. Now this implies S is a linearly independent subset of v. Right. So by the second corollary, by corollary 2 of replacement theorem, theorem, S can be extended to a basis for V. So we are done with the results on the dimension of subspaces.